Hello everyone. In this video we are going to talk about boundary representations. So if you have an image or object and you want to represent or describe the boundary, specifically represent the boundary like a binary image or anything, how can you basically represent it? Because you might say, yeah, with edges, right? So I have an image like a puzzle piece like that, and this is basically the boundary of it. True, these are all those edge points, but clearly if you want to track this and represent it, if you say, hey, the way I represent it is with a lot of edge points, that is not easy to keep track of and to represent mathematically. It takes a lot of computations. So what you want to do is come up with a way to mathematically represent this instead of saying just a bunch of points x and y. So here we're going to look at two algorithms. One of them is MPP, which is the Minimum Perimeter Polygon, and the second one is called Signature. And so the material here are again taken from pictures and the code taken from the book Digital Image Processing by MATLAB by Rafael Gonzalez and his colleagues. So the first thing we can do is we can represent the boundary of anything literally with a polygon as long as the sizes of the sides for the polygon are small. We can represent anything, even if it's a circle. If you look at the CAD software, even in a CAD software, you see that the circle is really a polygon, but the number of sides is very large, okay? And if those sides are small, you might not even easily be able to distinguish between a polygon and a circle. You have to zoom in. So polygon is really what we can use. And now, if of course the number of vertices of this polygon is equal to the number of points on the edge map, then of course you get an exact representation instead of approximation. But the goal is to be able to reduce the number of edges of the polygon and make it a little bit rougher, something like this, but with a way less number of vertices right here, because here you might have, I don't know, like 500, 1,000 edge points, but or less. And here, if you look, you only have just a few corner points, and this to a good extent captures the overall shape of your part here, right? You see this one and this one kind of you see the concave parts, the convex part to a huge extent. You might lose some accuracy in this area here, and again, if you basically change the number of edges, you might be able to get closer to it. But here, this shape and this shape are relatively close to each other. So here has, I just counted 23 vertices, while this one is going to have a lot more than 23 vertices. So, but the question is, if I can represent this shape with a polygon, which polygon is the polygon to use? Because there could be so many different polygons that you can choose to kind of represent this shape approximately. Which one of them is the best one? We're typically looking at the ones with minimum size, right? And size is defined in different ways, like what? Area, perimeter, and so on. And the one that is typically accepted in literature is minimum perimeter. So the polygon that can represent this with minimum perimeter, right, is one of the ones that is very accepted and common in the literature. So we use this method called MPP. And how is it done? So here, let's say this is the edge map of my binary image or any image. And what you do is, first, you choose a bunch of cells, a bunch of pixels in the image, right? And not just pixels, I mean, they are like super pixels, cells, that your edge is completely confined to, or it's inside of it, right? So you see here, this gray shape here, these gray cells, right? If you look at them, your real edge profile is inside the outer cell, and it's outside what? This inner cell, huh? So the first thing is to find that. So find this cell, these gray ones, and now what? Now that you have it, it's time to pick the vertices. Okay? It's time to what? It's time to pick the vertices. So, what do we do here? If you look, this is the same cell here in this bottom left shape. These gray ones are the same cell that I had, and this kind of black area is the interior of it. So now what we do is, in this interior area, in this black area, interior area, we find all of the corner points. Okay, so you see all of these corner points are shown with black and white. Now some of these corners are convex corners, which you see with white dots, and some of them are concave corners, which you can see with black. So here you have to have an algorithm to detect corners, which you can use, for example, Harris corner detector, or you can just, based on the location of these cells, you can find them directly. But the important thing is to distinguish between a concave one and a convex one. So how do I distinguish between these two? And I'm going to talk about it. And then you have to what? You have to, what you do is, for the concave ones, the black ones, instead of the concave ones, you displace them to their mirror image on this cell boundary. So look at this black one. I displace it to what? To its mirrored image with respect to this gray area, right? With respect to these cells. So this comes right here, right? Or this guy, again, if you mirror it, it comes what? It comes right there. This one here, it comes what? It comes here, mirror. This one comes here, right? You clearly can see that. This one comes here. This one goes there. This one comes here. So you get what? You get this set of black ones that you see in the last image on the right, on the bottom right image. You displace all of the concave ones. And now what? You connect all of the convex and concave together, and you get what? You get this approximated polygon. And if there is a vertex, whether concave or convex, that is left inside of this closed contour, like this one, you simply neglect it. Okay, so you connect them together back to back. You connect each one to its closest neighbors, right? And then, as I said, if something is left inside this, you just simply ignore it. You are not going to connect to that. Okay? Yes? So this is our overall algorithm. Now, as I said, we need to know how we go to distinguish between a convex and convex, and how to find whether something is outside the contour or outside the line or inside the line. Okay, so that is the second thing is we need to discuss. So first of all, what is the difference between convex and concave? If I zoom in, I can explain that to you. So look here. Here, if I have this point and this point and this point, right? And my goal is to find what kind of vertex is this. So what do I do? If I connect these two together, you see this is on this outer side. Yeah? Similarly, I can go about, again, this one here. So if I want to detect this one, I connect the two that are close to it, this one and this one. Again, you see this is outside. But if I do it for a concave, like what? Like this one, then if I connect this to this, look, it is on the inside of it. If I do it for this one, look again, It is what? On the inside of it. Look here, these two, it is what? It is on the inside of it. You see? Okay? Or here, it doesn't matter. If even after you displace them, like I want this. So I connect these two, you see, it's inside of it. But if I go for this one, when I connect these two, you see, it's on the outside of it. Okay? So the convex ones are outside the line, the concave ones are inside the line of the line that connects the 2 points on the boundary before and after them. So how can I distinguish that mathematically? Because yeah, it's easy to visualize it, but mathematically, the way you do it is using this matrix here. So if I have 3 points A, B, and C, where X and Y are shown with XA, YA all the way to XC, YC, if I form this determinant, 3 by 3, and if I calculate this 3 by 3 determinant, if this determinant is positive, that means what? It has two meanings. It could be 0 positive or negative. The fact that this is positive, negative, or 0, it has two meanings. The first one is that the arrangement of points A, B, and C is counterclockwise sequence. If it's negative, that means it's a clockwise sequence. If it's 0, that means they are on the same line. Also, another way to say it is this. If it's positive, it means what? It means that here you can see if point C is on the line on the positive side or on the negative side of the line connecting points A and B. Okay, so if I want to check whether this C is on the line connecting A to B or on the positive side or on the negative side of it, again, I can look at the sign of what? This determinant. Let me give you a numerical example that might make it more interesting. So here, let's say we have this coordinate frame, and we go with 2 points here, A and B. Let's say this guy is 1 and 1, and this guy is 3 and 3, right? So this is point A, this is point B. I connect them with a line, and here I consider several points. One is this point right here. I call it C, and this C is basically 1 and 3. Then I have point D here, which is 3 and 1, right? You see each one of them is on one side. And I also consider this point here, E, which is 2 and 2 on the line. So here I'm going to calculate the determinant of X of A, Y of A, and 1, as well as X of B, Y of B, and 1, and then X of C, Y of C, and 1. Okay, if I do that, see what happens. So for point C, that is on this left side, we have what? We have 1 and 1, we have 3 and 3, and we have what? We have 1 and 3, right? So if you use the Sarus's method, how much would you get? So the value is going to be positive 4, right? So you see for this C here, this point, the value is what? Positive 4. So that is on the positive side of this line here. Now let's go ahead and calculate it for point D. For point D, this 1 and 3 will be swapped, right? So this time I'll change that. I make it a 3 and 1. So this is going to be X of D and Y of D, right? And if I calculate that, again, using the Sarus's method, you'll get what? You get negative 4, right? And that means point D is on the negative side of this line. So this guy is what? This point is going to be negative 4. And here, if I go about calculating point E, which is on the line, as you know, if I just plug in 2 and 2, you can easily show that this determinant is going to be what? It's going to be 0 because you have a 3, you have a, let me just replace them. right? So if you do 2 and 2, that's a 3, that's a 6, that's 9, and 2 is 11, minus 6, that's 5, minus 2, minus 3, you get a what? You get a 0. Okay, so for this point is 0. So you see, E is on the line, C is on the positive side, E is on the negative side. And the other thing was, if I go by order A, B, C, look, if I go A to B to C and coming back, if I go this order, A to B, B to C, C to A, it says the order is what? Counterclockwise sequence, which you can clearly see going from A to B to C back to A is clearly what? Counterclockwise. While on the other hand, if I go from A to D, right, or A to B, sorry, you have to go from A to B first, then to the third point. So you go A to B, then go B to D, and then go back. Now clearly you see this order is what? Clockwise, while the green one was what? Counterclockwise. And for E, there is no order, they are on the same line. So this is how you can distinguish what? You can distinguish between a concave point and a convex point here, right? Because here, if I go from here to sorry, let me go back. If I go between these 2 points and then I look at this point in the middle, right? So look at the order. This is what? This is counterclockwise, right? If I do this one again here, I connect these two, I go back to this, and then I go back. So I put the test point in the middle, right? Let me close that. Here, again, you see that for the concave point, whether it was this one or this one, the order was counterclockwise. But if I go for, let's say, this point in the middle, if I connect these two, and then go to what? Go to this point, and then go back, clearly you see the order is what? Clockwise. Or again, look at this one. I connect these two, and then what? Look, here. I go clockwise. So I can see it by positive or negative side. And also here, as I said, we neglect this point. How do we know we should neglect this point? Because when I connected these guys together, this guy stays on the interior side or on the negative side of this line, not on the outside or the positive side of this line. So after I connect them, if there is any point on the negative side of these lines, then I can simply what? Ignore it. So you see how important this determinant is in order to for this algorithm to work. And one last thing about this algorithm is the cell size. So the size of the cells, the thickness of this gray area is very important in how good this approximation gonna be, how close this approximation is to the original edge map. Here, in this shape, you see that the pixel, the cell, could be selected as what? It's impossible to do it as 1 pixel because the thickness of each one of these is 1 pixel. So clearly, the size of this cell is not what? Is not 1 pixel, it's several pixels, right? So in this case, I don't know, it could be 8 pixels, 10 pixels or something, right? But could I use a narrower gray area? Yes. If I used a smaller, narrower area, probably I could go with something like this, okay? I could go with something that is far thinner, like that. Okay, if that's the case, that means those convex and concave points that you extract are going to be closer to each other, right? So here you cannot do it. So here you have to do it with basically several of this because the thickness cannot be preserved. So here you have to change it in several areas probably. Okay, so you're going to get more vertices. If you try to keep it thinner, then in some areas you have to break this in several points, right? As you can see, so I can what? I can keep that small thickness, right, of 2 pixels or 3 pixels. So the thickness of the cells is, or the size of the cells is very important. Here, to show you the effect, I have generated some pictures for this leaf, for this maple leaf. You see the image is binary, as you can see, and the original edge map is overlaid on the image in red. So this is what I have, and now instead of this red maple that has lots of edge points, I want to approximate it with a polygon with a lot less sides, or a lot less points. So here the cell size is 2, like bare minimum. Basically, you're only going with 2 pixels width for those gray areas, which is the smallest you can go. And you can see that the shape of the polygon is very, very close to the actual edge map. It's very good. But here, if I allow for a thicker cell size and smaller number of edges, you see that still it's good, but you lose some accuracy in some places. Okay, still not bad. So you can see here you lost that line, kind of curved out. And if you go for some bigger one like cell size 9, now you clearly are losing some information here, like this portion here. You see it's gone, right? Or all of these small variations are gone, of course, because you are allowing for a rougher estimate. So the number of cells is very important. Now let me show you the code here. And this code I have not written myself, okay? This is coming from the book Digital Image Processing by Gonzalez. So all the credit goes to him and the people who wrote this code. And I'm going to share these codes for you under the video description. And you can find these codes also on GitHub. On GitHub, if you look for these codes, you can find them as well. So they already shared it with public. It's not like I'm taking their code. So this is the code. You see, you pass to it an image I, which is a binary image. It has to be a binary image. And you give it the cell size, and it gives you X, Y, and R. Where X and Y are clearly what? As you can see, these are the coordinates of the corners, vertices of the polygon. And R is the region extracted from that image. Okay? So here I have my code. I read the image leaf.ping. I got that image and convert it to binary. Then here I use the command bw boundary to give me the edge map of that boundary of that binary image, right? If your image is binary, you don't need the command edge. You can use the bw boundary. And it gives me B, and this B, the boundary is going to be in a cell format. So here I converted it to what? To matrix. So now B is going to be just a bunch of X's and Y's. And now what I do is, one time I pass that image, and you might say, why do you need B? B is used to draw this red curve for you. Okay, so B is not the result that I have in this 3, right? B is that red curve overlaid over the image. And you can see it here, that I showed the image, and then I did a hold on, and then I showed B1 and B2, X and Y in red. So one time I pass my binary image to the command image to min per poly, min perimeter poly, with cell size of 2, 1, 4, 1, 9. I got the coordinates x2, y2, x4, y4, x9, y9, and I show them here. So let me go ahead and run that for you so you can see the results, right? There we go, here. Okay, so here, original image, cell size 2, cell size 4, cell size 9. And it's interesting here on this tip point here, you lose some information, okay, if you use a bigger cell size. Now, one thing I want you to pay attention to is this. Look how many points your original edge map does have. 1494, about 1500 points is used to show that red edge map. But if I use a cell size of 2, which is the finest one, I only need 152 points for the polygon. If I use cell size 4, I have 84, and if I use 9, I have 41. Imagine that, right? So while this guy needs about 1500 points to define it, this one, which is still very good, I mean, like, you don't need to go as good as that and as bad as this one, which is still very good, is only using 80 points for the polygon, right? So imagine comparing 1490, what? It was 1494 against 84 vertices, right? Imagine how much reduction in memory and computation it is to keep track of this or describe this versus to describe that. And this guy was 42, this one was 150 something, right? So that's why this minimum perimeter polygon is really saving a lot of memory and computation for you. Okay, so this is the first algorithm or method. The second method, which I really like also, is called the signature of a profile or a boundary. And this is really good because this is even better than previous one in terms of reduction in computation. In the last one, you needed a lot of still a lot of X and Y points because this is 84 really times 2 pieces of information, right? Yes. Or if you want this accurate one, this is that one times 2. Still not bad, but it's a 2-dimensional representation of the shape. One thing you can do is use a 1D representation for a profile. Really? How? If you use a polar coordinate, if you describe the radial distances of different points on the boundary from an interior point, typically the centroid, arrange for increasing angle. What does that mean? So let's say here, if this is the boundary I want to describe, and this is the centroid point, so I draw, basically, it's like, imagine you have a scanning LiDAR. So you draw this line, and on this direction, on this theta of 0, you measure this radial distance r. Yes? Then you draw this line at this angle, and then again what? You calculate distance r for what? For this angle theta, right? And then you do that more and more and more. So per each one of those angles, you measure what? You measure the radial distance from the center point to what? To each one of these points on the boundary. And then you plot what? R versus theta, right? So you basically do a polar plot. Well, in this case, of course, since it doesn't matter what angle, R's are all the same, your R theta plot is clearly going to be a flat line, right? So if you see this signature of R theta, this polar curve is clearly for a circle wherever you see that. While if it's a square and you do that, now you don't get the same thing. So here, as you go from here to here, you see that you get the distances bigger and bigger and bigger. And then as you go from this point, so starting from this right point to that point, the distances are going up more and more. And then as you go from here to this point, now they start to shrink. And then it repeats again. It goes up, 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 and then it goes down, down, down to minimum. So the behavior that you see is like this. Not like it's a smooth sine wave because you have a sudden change, right? But clearly you see this up and down behavior. So that kind of showing me the square behavior. And these sharp corners here are showing me that your profile really has 4 sharp corners. When you see a sudden change in this profile, that means a sudden change in the actual profile. And that is referring to these 4 corner points. Okay, so you see for any shape you can create this signature, and this is a beautiful way to represent any boundary as a 1D piece of information. And you might say, how come 1D? Here you still have R versus theta. How come it's 1D? The reason is this: we only really need R, because the theta goes anywhere from 0 to what? To 360. So the theta values are always predictable. They are from 0 to 360. So if I only have the R values, and I know the first one is for theta of 0, the last one is for theta of 360, if I just store the R values, then I can just plot them versus 0 to 360. Okay, so I just need really the R values. That's all I need. That's how you can make it 1D, and this is really a good compressed form of the boundary. And could you make it, do you always need 360 data points here? No, because if you want, instead of scanning for every single degree, you might skip every 3 degrees, okay? If you go every 3 degrees and scan, yeah, you get this a little bit probably rougher, right? So here you might have a little bit jumpy kind of behavior, but still you can catch the overall thing, and now you just need 120 data points. Okay, so as long as you do one full scan, and again, this is like a LiDAR, like a scanning robot, that you put it there and it keeps rotating and measuring all these distances and creates a map of the environment from inside. That's what a signature is. Okay, so now let's talk about a few technical things that we need to know about this method, because it looks so easy and very intuitive, but there are a few things that we need to know. One is, the good thing about this method is it is a translation invariant, okay? So if the circle was not here and it was here, or it was here, it doesn't matter as long as we can have the same centroid position with respect to the profile. Then the location of the profile doesn't matter. So the profile that you will get is always the same regardless of the location of the profile. So by nature, this method is translation invariant, but that's not enough. It also has to be scale invariant, and it has to be rotation invariant. So if this square is like, instead of that size, if it's a little bit smaller, or if it's rotated, still give you what? The same profile that is for a square, regardless of the size, location, or the orientation. How can we make those two happen? For a scale invariant, of course, if instead of this, let's say, circle, I have this circle, right? Then you'll get this line a little bit above it, right? Because the R values are going to be a little bit bigger. Or in this case, the case of the square, they're going to be similar. So they're going to probably start something like this, right? Because you're dealing with bigger distances. So everything is shifted up. So one thing I can do for this is to divide all of these values by their maximum and bring the range between 0 and 1. So if I divide, let's say this is 75. If I divide all these values by their maximum, which is 75, or here all of them by 50, then both of this green and the blue plot will be the same as this red plot, where the maximum value is 1. So if I see max value at 1, that means clearly what? That's a circle. And here too, again, if I divide the blue one by 35 and if I divide the green one by, I don't know, maybe 50, then it's going to be the same, but what? This maximum here is going to be 1. So it goes from 0, not 0, maybe like 0.1 to 1 or something like that, or 0.5. You know the ratio, huh? It's the ratio between this one and this one, which is basically 1 over square root 2. So this is like 0.707. Okay, so that is going to be what? That is going to be the square for a, the profile for a square, the signature for a square, right? So normalization, if we normalize the data, we can get what? We can get it a scale invariant. Now, one thing important is, if the edge map has noise in it, if this boundary has some problems, have some noise, for instance, in this case, it is a square, but one pixel here is missing. Instead, you have a pixel here. So you have all of these blue points, but instead of this red point, your red point is there. There is some noise. That pixel is missing, that pixel is instead over there because of noise in the image. Now everything is going to be screwed because now you have an outlier data where everything is divided by this much bigger distance that should not even exist. So if you divide by maximum of the data, the maximum distance, the maximum R, could be basically ruining your normalization because you might have noise. So one good idea is, instead of dividing everything, instead of saying R divided by max of R, we use some measurement here in the denominator that is more robust to noise. And one clear thing is what? The standard deviation of R. This is much better, right? You can divide by that, or if you have a median or something. But typically dividing by standard deviation, right, is very common in machine learning and image processing. And when they want to center it around 0, then they subtract from the mean. But here you can divide by standard deviation. That is a lot more robust. Okay, so that's one thing. Now, how about the rotation invariant? How would you make it robust to rotation? Is if your start point is always the same point. What does that mean? Well, here you might say it's easy. I always start from theta of 0. Right? So I always look on my right side and go for that. Yes, or here. Okay, I always look at my right side and I start scanning from there. But the problem is, if you have this scenario now, the shape is rotated. If you want to do the same thing, now you start from here. And clearly, the location of this red circle with respect to the red square is not the same as the location of the blue circle with respect to the blue square. Right here, this one is in the middle of the edge, this one is not. So in this case, you will get a shift in the data. In this case versus this case. So for blue, it might be like this. And for red is probably you are already starting at some, so when you go here, you go down first, then you start going up. So you are starting, like, for instance, from here, something like that, or from here, then you go up. So it goes something like this. Okay, so how can you get rid of that shift? And for this case, it might be simple, a simple shift, but if the profile is a little bit more complicated, it might not be a very easy shift to register, okay, like that. So if I can select the same relative position of the start point with respect to the profile, that kind of guarantees me a rotation invariant. How can I do that? One way to do it is to use the major eigenaxis. So if you know from the binary operations on images, which I have a video on this playlist, if you have a shape like this, there are lots of things you can do on this boundary. One of them is to find the eigenaxis, the axis of the minimum and the maximum variation. So this is one of the eigenaxis, this is the other one. So if I start on this eigenaxis that has the biggest variation, and I start on the furthest point, so I start here, then that's good to go, right? Or for the sake of this square, if I would, again, in this case, the eigenaxes are quite a bit similar, right? So you have this one and this one probably, or this one and this one. So if you use those, then you can have the same relative position, right? So it needs some computation to do the eigenaxis and start on the eigenaxis all the time, but that makes it what? Robust to noise. One last thing I need to emphasize about this signature method, and then go and show you the code, is the important thing is this, that the pixel should only, the edge map should only be 1 pixel thick, and it has 1 layer. That is very important. So if you have a profile like this, then clearly the only thing, if you find the centroid, the only thing that you can really show is this interior scan. Okay, yes. Or if you look at, because now you have a multi-value function here, if I scan along this direction, I get this point and I get this point. So now you're going to get two curves, and that's not really what the signature is about. It's to get one single curve and not a function with several values for the same x, because that's not the definition of a function. For each theta, you should have only one r, not two r's or three r's. So you should have only one closed profile and not several inside each other. So if I show you the code now, this is this code called signature. Again, it's coming from the GitHub, and it's coming from the book Gonzalez by Gonzalez. So this is the code, and you pass to it what? You pass to it B, which is a boundary. So B here is not an image. It's a boundary, and it has to be NP by 2, where NP is the number of points, and 2 is first column X, second column Y. So you pass to it, what it gives you is x0 and y0, the location of the centroid, or this center point for the scan, as well as ST and R, where ST is basically those R values, right? And angle is those scanned angles. Okay, so maybe your start angle is not always 0, as we said. So here it gives you those angles and ST, and here I wrote a code to test it. One time for a circle, one time for what? For a square. And here, let me show you the square one. You see, so I defined the square between x and y of 50 and 100. And you clearly get what? The beautiful signature of a square. And another thing I can do is to comment out the square and uncomment the circle. And if I run it again, you clearly can see what? The flat line. Now see here, you see small variations, but these are really not happening, and basically I get a start flat line. Okay, just to show you one more interesting thing, I added the leaf as well. So here I read the leaf again, I got the boundary for it in terms of B, which is a NP by 2 matrix. Remember, NP here is 1494. And then I pass it to the signature command. So you can see this one, that is an interesting one. So look here, this is what? This is the signature of the leaf. Now here you need to basically rotate this and make the axis IJ, so it shows the leaf upright. But here is what? This is the profile for a leaf. And you see here, you only go with 360 values. And if you want, you can downsample it. You can get every 1 or 2 data points out of this 360 and get a rougher approximation of that. But clearly, this is the profile of a leaf for you here. Okay, so as I said, I'm going to share these files for you, as well as the picture of the leaf. And hopefully, it is showing you something useful for representing boundaries of images, and I'll see you in the next video. Thank you.